Today we're going to begin the discussion of modular arithmetic. It's one of the most important applications of number theory. So let's just start with the definition. So let m be a positive integer. Then for any integers a and b, we say that a is congruent to b modulo m, and write a is congruent to b mod m like this, if m is a divisor of a minus b. So in other words, a and b differ by some multiple of m. The smallest non-negative integer that a is congruent to mod m is called the least residue of a mod m. And you'll note that the least residue is just the remainder in dividing a by m. So for example, 17 is congruent to 2 mod 5 because 17 and 2 differ by a multiple of 5. Or in other words, when you take 17 and you divide it by 5, you get 3 with the remainder of 2. So the least residue is just the remainder. Substitution laws. Okay, this is what makes modular arithmetic work. So suppose a is congruent to b mod m and c is congruent to d. Then a plus c is congruent to b plus d, and a minus c is congruent to b minus d. In other words, you can just substitute in equivalent values without changing the value of the sum or difference. And the same thing works for multiplication. If a is the same as b and c is the same as d, then a times c is congruent to b times d. And then by induction, we would have the following. If a is congruent to b mod m, then for any positive integer n, a to the nth power is congruent to b to the nth. After all, a to the nth just means a times a times a times a, and just use property 2 over and over. I would just substitute in b for each one of those a's. Okay, so for example, 283 plus 702. Well, 283 is 3 more than 280, so 283 is congruent to 3 mod 7. 702 is congruent to 2 mod 7, being 2 more than 700. So this expression is congruent by substitution to 3 plus 2, which equals 5. Or 283 times 702. Again, I just substitute in the equivalent smaller values, and 3 times 2 is 6. All right, let's look quickly at a proof of the substitution laws. So if a is congruent to b, this means that a differs from b by a multiple of m. So let's say a is b plus m times k, and c is congruent to d. So d plus ml for some k and l in the integers. And so if I want to look at property 1, a plus c is then equal to b plus mk plus d plus ml, and then using associative and commutative laws and the distributive law, we would get b plus d plus a multiple of m. So a plus c and b plus d differ by a multiple of m. Which means they are congruent, since k plus l is an integer. Likewise, in property 2, if I want to look at a times c, that would just be this product, which is, using the distributive law, bd plus mkd plus bml plus mkml, and then using the distributive law once more, I factor out an m, and I've got kd plus bl plus one of the m's is going to remain here, so kml. And again, we see that a times c and b times d differ by a multiple of m. So ac is congruent to bd mod m, since this quantity right here is an integer, kd plus bl plus kml. And as I noted earlier, part 3 just follows by induction. Okay, let's do a couple examples. So if I want to find 47 to the 50th power, the first thing I'll do is substitute in that 47 is congruent to 2 mod 5, being 2 more than 45. And so 47 to the 50th is the same as 2 to the 50th. And next, I want some power of 2, which reduces nicely mod 5. So I can either say that 2 squared is 4, which is negative 1, or I could observe, let's see, 2 cubed, that's no good, 2 to the 4th. 2 to the 4th is 16, which is 1. I could use either one of these relationships. And so let's say we use the 2 squared one, since I wrote that down first. So this is 2 squared to the 25 power, mod 5. And notice I'm just writing mod 5 once to the right. I don't have to squeeze it in right here, although there's no harm in doing that. And we have a negative 1, substituting in that 2 squared is negative 1. So negative 1 to the 25th is just negative 1. And so if I'm asking what's the least residue, I would say 47 to the 50th is congruent to 4 mod 5. 2 to the 100th. Well, this time I see very quickly that 2 cubed is 8, which is 1. So 2 to the 100th is 2 cubed to the 33 power. That gives me 99, and then I'd have one more 2 left over. 2 cubed is 1, so this is just going to be congruent to 2. Or 2 to the 100th mod 17, we've got 2 to the 4th power is 16, which is negative 1. So let's just stop right there. And thus 2 to the 100th is 2 to the 4th 25 times. So 2 to the 4th, I substitute in negative 1, raise that to an odd power, and I get negative 1. So the least residue would be 16. Okay, pretty neat how quickly you can work with these huge numbers. I mean, 47 to the 50th, that's a huge value, or 2 to the 100th. So in modular arithmetic, you can do exponentiation extremely rapidly. Theorem. Suppose I have a polynomial with integer coefficients, and I want to compare f of a and f of b. So if a is congruent to b mod m, then I claim you get the same value when you evaluate the polynomial. So f of a is congruent to f of b mod m. And again, this is just a substitution type of law. So after all, a congruent to b mod m implies that a to the k is congruent to b to the k for all values of k going from 0 to n, and you have the same coefficients each time, so then we would have that ck, ak, is congruent to ck, bk mod m for k going from 0 to m. And why is that? Well, a to the k is congruent to b to the k, and ck is certainly congruent to ck, so again that's just substitution law. And then finally, we've got these, that's an n right there, n plus 1 numbers, and we're just adding them up. So if I just add these numbers, k equaling 0 to n, then by the additive substitution law, it's the same as adding up these numbers. But this is just f of a, and this is f of b. Another elementary congruence property is the following. On this one, it's a little different than the others because I'm changing the modulus. So if I start with a being congruent to b mod m, and I let d be any divisor of m, then I claim we still have a is congruent to b mod d. So what's going on here? So when I say a is congruent to b mod m, that means that m is a divisor of a minus b. Okay, now we're given that d is a divisor of m, so since d divides m, and m divides a minus b, then by the transitive law for divisibility, we get that d divides a minus b. That is, a is congruent to b mod d. It's as simple as that. Okay, congruence mod m is an equivalence relation on the set of integers. So what is an equivalence relation? It's a relation that has 3 properties, and I've enumerated them in this theorem. There is a reflexive property that for any integer a is congruent to itself mod m. We need to have a symmetric property. If a is congruent to b mod m, then b is congruent to a mod m. And then finally, a transitive property. If a is congruent to b and b is congruent to c, then a is congruent to c. And all of these are very elementary, so let me just be very terse in the proof, and you can write down the details. So in part 1, what's going on? To show a is congruent to a, I want to show that m is the divisor of the difference. Well, the difference is 0. M divides 0 is all I need to say there. To show it's symmetric, what's going on there? Well, if m is a divisor of a minus b, then m is a divisor of b minus a. Nothing going on there. And then in part 3, if a is congruent to b mod m, so m is a divisor of a minus b, and m is a divisor of b minus c, then m would be a divisor of the sum of these two things. That is, what do you get when you add up these two things? The b's cancel, and you get a minus c. And this means that A is congruent to C mod M. Okay, so that's really the core of the proof, and you can put in a few more details there. So anyhow, you've got a nice equivalence relation on the integers, so it partitions the integers into different equivalence classes. So an equivalence class would be a set of integers, all of which are congruent to one another. And we introduce some notation for that. So congruence partitions the integers into equivalence classes of the following form. So I'll use a bracket. I'll put a typical integer in that equivalence class in here. That's the value A. I'll put a subscript m to denote the modulus is m. So bracket m is the equivalence class containing A, and it's the set of all numbers of this form, where you fix A and you add to it any multiple of m. So the set of all objects of the form A plus k times m, where k is an arbitrary integer. So we call these residue classes mod m, or congruence classes mod m. Okay, with the idea of a congruence class, we can then define the ring of integers mod m, and I'll denote that z sub m like this. So the ring of integers mod m is just the set of all congruence classes. Well, how many different congruence classes are there? Every integer is either congruent to 0, to 1, 2, all the way up to m minus 1. So altogether we get m different classes, equivalence classes, or congruence classes, and we just use the bracket notation right here. So Zm is a set containing the m distinct congruence classes. Now I want to call it a ring, so to call it a ring, we have to have an addition law and a multiplication law, and we define those as follows. If I want to add the residue class A to the residue class B, all I do is I take the representative for the class and I add them together, and I get this class A plus B. Or if I want to multiply two different classes, I take the representatives for the classes and I just multiply them together to get the new residue class. Now, the first thing you have to ask yourself is, well, is that addition and multiplication law well defined? After all, there's lots of different representatives for a given residue class. Okay, well, I claim by the substitution laws, that's theorem 5 here, substitution. Probably didn't have a number up in the previous slide, that addition and multiplication are indeed well defined. So suppose we have different representatives like this, an A1 and an A2 representing the same class, and that you have a B1 and a B2 representing the same class. Okay, then if I want to look at A1 plus B1, well, the definition says I should look at this. But if I want to look at A2 plus B2, the definition tells me, well, that's A2 plus B2. So it looks like I'm getting potentially two different answers coming out. So I'm adding the same two residue classes, and yet the definition's telling me to look at two different answers here. But what do we know? Well, if A1 is the same as A2, A1 is congruent to A2. And B1 is congruent to B2. And so the substitution laws tell me that A1 plus B1 is the same as A2 plus B2. Aha! That means that the answer I got over here is in fact the same as the answer I got using the A2, B2 representatives. So we're lucky. Well, not lucky. We needed that. We get exactly the same answer. And of course, if we had done multiplication, it would have worked exactly the same way as well. So ZM is in fact a ring. We have a well-defined addition and multiplication. It's a ring with a 0 element being the residue class containing 0. It has a unity element 1. And I'll leave it as an exercise to actually verify the different axioms for a ring. They follow immediately from the corresponding properties for the integers. So we're talking about the commutative law for addition, the associative law for addition and multiplication, and the distributive law. So all of these types of properties you can write down very easily to show that they follow from the properties from Z. So in fact, the ring of integers mod M is a commutative ring with unity. Now there's two different ways to think about problems when you're doing modular arithmetic. And it follows from this fact that A is congruent to B mod M if and only if the residue class A is the same as the residue class B in the ring ZM. So there's 2 points of view. You can either think of working in the integers, which is an infinite set, and just think of there being congruences mod M with this infinite set of integers, or you can think, aha, I'm living in a finite set. I'm living in the ring ZM, which is just a finite set with M objects, and I'm doing arithmetic in this finite set. So for example, the following are the same problem. Solve the congruence x squared congruent to 1 mod 6. Or B, solve the equation x squared equals the residue class 1 in the ring Z6. So in the second vantage point, I'm thinking, oh, I've got 6 objects, each of which are these congruence classes. And in part A, I'm thinking, oh, I'm looking at integers, and I'm trying to find some integers whose square is congruent to 1 mod 6. And of course, the answer is going to come out the same. We really only have 6 different values mod 6, and you just test them by trial and error as easy as any way here. So 1 squared, that would certainly work. 2 squared fails, 3 squared fails, 4 squared fails, 5 squared, well, 5 is -1, and so that works as well. And so you just get these 2 values, plus or minus 1, mod 6. And likewise down here, we would get x is plus or minus the residue class 1. Or you could write it like plus or minus 1, 6. Either way would be fine there. Now the notation of using the bracket sub m can be rather cumbersome, and so there's 2 simpler types of notations we frequently use in modular arithmetic, or when we're working in the ring Z mod M. You can just put a bar over the value, and so ZM you would represent with 0 bar, 1 bar, up to m minus 1 bar. So the bar just represents the residue class. And if you like, you can just drop that all together and just denote Zm as the set of integers from 0 to m minus 1. In particular, if I'm writing a multiplication table, I would just use this type of notation. Just use those as abbreviations for the residue classes. So here's an example. If I'm working in Z4 and I want to write down the addition and multiplication tables, I just use the integer representatives, 0. These are kind of the canonical representatives, 0, 1, 2, and 3. Now, there's another way to think about this multiplication table here. You can actually think of it being some strange new multiplication law for the finite set of integers 0, 1, 2, and 3. So don't think of them as residue classes. Just think of it as these set of integers, 0, 1, 2, and 3, on which you have defined a new type of multiplication and addition law. And it would turn out that for those new laws you're defining, all of the algebraic properties hold true, associative law, commutative law, etc., etc. So that's another way you can think of this addition and multiplication table, if you want to treat these as actual integers rather than abbreviating residue classes.